This will be the first lecture out of chapter 3. So this is typically one of the hardest chapters for most students in this class, so definitely recommend try to pay really close attention in these lectures and definitely study this material. It's not that difficult. There's no calculus in this. There's no differential equations. There's not even any algebra in this chapter. It's just all addition, subtraction, multiplication, and division, but it's a difficult chapter in terms of setting up problems for most students. And it's all math, a lot of math, total calculations in this chapter, not much else. Okay, so basically start by this concept. So how do chemists count things? So how do you count things? So if you had 2 cats, you could tell someone that you have 2 cats, or you could say I have a couple of cats, right? So a couple is a unit that you could count by. Or if you have 12 eggs, you could say I have 12 eggs, or you could tell somebody you have a dozen eggs. And most everyone would know what you're talking about because most everyone knows what a dozen means. So it's convenient to use different units to count things. So 2, you could say a couple or a pair, right? 10 years, you could say 1 decade instead. So 13 donuts, so that would be a baker's dozen, right? 1 baker's dozen. If you've heard the Gettysburg Address before, 407 years ago, what does that mean? So what is a score? So a score is 20 years. So that would be 87 years. So what's a gross? A gross is 144 of something. So there's all kinds of different units out there. So for those of you who are coffee drinkers, I don't drink coffee. I love the way it smells, but never acquired the taste. But maybe you like to drink coffee, so a short espresso would be 8 ounces, right? Or if you want a tall espresso, that would be 12 ounces. Or if you want a grande espresso, that would be 16 ounces, but maybe that's not enough for some of you. You can get bigger, right? You can get a venti, that would be 20 ounces, or for the serious coffee drinker, you could get a Trenta, that would be 31 ounces. So again, just different units that people use to count things by. So chemists tend to not count things by dozens or couples or pairs, especially if we're talking about things like atoms and molecules, right? Why not? Is because atoms and molecules are extremely small. If you had a couple of atoms, you couldn't see them, right? If you had a dozen atoms, you couldn't see them, so not even with a microscope, because they're way, way, way too tiny. So chemists tend to count things by what's known as the mole, or abbreviated MOL. So 1 mole is defined as the number of carbon-12 atoms in exactly 12 grams of carbon-12. So we've seen something else that's defined in terms of the carbon-12 atom, if you remember. So what else is defined in terms of the carbon-12 atom would be atomic mass units, or AMU. So the mole and atomic mass units are both defined in terms of the carbon-12 atom. So how many atoms of carbon-12 are in exactly 12 grams of carbon-12? Right, a lot, a whole lot. So it's what's known as Avogadro's number. So Avogadro's number is 1 mole of something, and 1 mole of anything is this. This is how many carbon atoms are in exactly 12 grams of carbon-12. So it's a staggering number, right? So this is 1,000. So this would be 1,000,000. And so after 1,000,000, so this would be 1,000,000,000. All right, so there's about 7 to 8 billion people in the world, and we're not even close to Avogadro's number. So what's after 1,000,000,000 would be 1,000,000,000,000. All right, so the United States gross domestic product, GDP, is about 20.5 trillion. So that's how much the value of all of the goods and services produced by the United States in 1 year. And we're still not even close to Avogadro's number. So what comes after a trillion? So most people would not know what comes after a trillion. If I wasn't teaching this course, I probably wouldn't know what comes after a trillion. But what's after a trillion? is a quadrillion. And still not there, what comes after a quadrillion is a quintillion. And what comes after quintillion is sextillion. So there are 602 sextillion carbon atoms and exactly 12 grams of carbon-12. So that's an absolutely huge number. So for our purposes, we're going to round that. So this is how accurate the number is known to that many significant figures. So we're simply going to round that to, let's just say 6.022 times 10 to the 23rd. So 12 grams is not a lot, 12 grams. So one AAA battery weighs about 12 grams. A quarter weighs about 25 grams. So 12 grams of carbon is not a lot, but there are a staggering number of carbon atoms in that 12 grams. Okay, so you can all count by dozens and pairs, but let's see if you can count by the mole. So you just have to remember, a mole is simply a number of things. A dozen is 12, right? So if I say a dozen, what pops into your mind probably almost instantly within a split second is 12. If I say a mole, what should instantly pop into your mind is 6.02 times 10 to the 23rd, right? Okay, so if you had a mole of chocolate chip cookies, you would have 6.02 times 10 to the 23rd of them, right? And you would be set for life, assuming they never went stale. So if you had 2 moles of iPhones, how many iPhones would you have? Well, if you had 2 dozen, you would just take 12 times 2. You would have 24, right? So if you had 2 moles, you would just take Avogadro's number, 6.022 times 10 to the 23rd, and multiply it by 2. So I recommend you try this on your calculator. This is, some students have a difficulty knowing how to exactly use their calculator, especially when we get into exponents. So if you wanted to practice on your calculator, so that would be 1.204 times 10 to the 24 iPhones if you had 2 moles, right? So if you had 1.5 dozen pencils, how many would you have? Well, you could do it this way. Well, a dozen is 12 and half a dozen is 6 more, so that would be 18, right? Or if you were simply doing the math, a dozen is 12 and times 1.5, so you would have 18 pencils. So if you had 1 mole of pencils, how many pencils would you have? Well, you just have to keep in mind, again, a mole is 6.022 times 10 to the 23rd, and if you had 1.5 moles, and you take that and multiply it by 1.5. So that would be 9.03 times 10 to the 23rd pencils, right? Okay, so now rather than talking about objects, let's talk about molecules, something more related to chemistry. So if you had 1 dozen water molecules, so water molecules, H2O, right, 2 hydrogens attached to oxygen. So if you had 1 dozen water molecules, how many molecules are there? Well, there are 12 molecules, right? But how many hydrogen atoms are there? So if we have 12 water molecules, so I drew 12 water molecules here, so that's a dozen, right? So if you counted all the hydrogens, of course there are 24 hydrogens, right? Because there's 2 hydrogens per molecule, and if you have 12 molecules, then you have twice as many hydrogens as you have molecules. How many oxygens do you have? Well, there's only 1 oxygen per molecule, so if you counted up the oxygens, you would get 12, right? So one thing to recognize in formulas is the subscripts are molar ratios. Right, so if you have 1 mole of water, you have 1 mole of oxygen, but 2 moles of hydrogen. Well, okay, so that's a dozen. So if you have 1 mole of water molecules, how many water molecules do you have? Then you have 6.022 times 10 to the 23rd, right? Because 1 mole of anything is Avogadro's number, 6.022 times 10 to the 23rd. How many hydrogen atoms do you have? Well, there's 2 hydrogens per molecule, so you would have 6.022 times 10 to the 23rd, right, times 2. And how many oxygen atoms do you have? There's 1 oxygen per molecule, so 6.022 times 10 to the 23rd. If you had 2.5 moles of water molecules, how many molecules are there? Well, there's 6.022 times 10 to the 23rd in one molecule, but you have in 1 mole, but you have 2.5 moles. So you would just take that number times 2.5, right? How many hydrogen atoms are there? So there's 6.022 times 10 to the 23rd in 1 mole, but you have 2 moles, and there's 2 hydrogens per mole. Sorry, you have 2.5 moles. So you would have to take that 6.022 times 10 to the 23rd times 2.5, and then you would have to take that and multiply it by 2, since there's 2 hydrogens per molecule. And then in terms of oxygen atoms, 6.022 times 10 to the 23rd, and just multiply that by 2.5, since there's 2.5 moles, and there's 6.022 times 10 to the 23rd in 1 mole. Right? So hopefully that makes sense, and you can count by moles now. So we'll take another example. So if you had 1 mole of this molecule, C3H7Br. So if you have 1 mole of that molecule, how many molecules are there? So if we're talking about molecules, we're talking about the entire thing, right? So 1 mole of anything is 6.022 times 10 to the 23rd. How many bromines would there be? Well, there's 1 bromine per molecule. So there would also be 6.022 times 10 to the 23rd bromines, right? How many carbon atoms would there be? Well, you can see from the formula, right? It's in a 3 to 7 to 1 ratio, or in the structure that I have drawn out, you can see that there's 3 carbons per 1 molecule. So if you had this many molecules, you would have 3 times as many carbon atoms. And in terms of hydrogen atoms, if you had 1 mole, there's that many molecules, but there's 7 hydrogen atoms per molecule. So you'd have to take that and multiply it by 7, right? Okay, so again, just to reemphasize, if you're interpreting molecular formulas, keep in mind these are molar ratios. So this represents basically 2 numbers. If you had 1 single molecule, then there are 3 carbons, 7 hydrogens, and 1 bromine. So that formula applies to 1 molecule. That formula applies to any unit you want to stick after that. So if you wanted to stick a mole after that, then there would be 3 moles of carbon, 7 moles of hydrogen, 1 mole of bromine. If you wanted to stick a dozen after that, if you had 1 dozen of these molecules, then how many carbons would you have? Well, you would have 3 dozen carbons, you would have 36, right? So I've got 12 molecules drawn here. If you want to count all of the carbons, you would see that there's 36 of them. And if you wanted to count all of the hydrogens, well, if you had 1 dozen of these, then there's 7 dozen hydrogens. So if you counted all the hydrogens here, you would get 7 times 12. Or if you counted all the bromines, since there's only 1 bromine per molecule, then there would be 12 bromines, right? Okay, so C4H6O2, if you had 1 mole of that, then how many moles of carbon are there? There would be 4 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen, right? If you had 2 moles of that, there would be 8 moles of carbon, 12 moles of hydrogen, and 4 moles of oxygen. So it always has to stay in that ratio, right? 4 to 6 to 2 ratio. Okay, so lastly in this lecture, we'll talk about this concept of molar mass and formula mass. Basically, these are calculated the same way. There's just kind of a formality in what you call a molar mass and a formula mass, and we'll see molecular mass and molecular weight as well. So molar mass is simply the mass of 1 mole of any substance. So 1 mole of carbon-12 atoms would mean 6.022 times 10 to the 23rd carbon-12 atoms has a molar mass of 12 grams, right? That's how the mole is defined. Okay, so what about if it's not carbon? So if we took iron, for example, if you look at the periodic table for iron, it's atomic number 26. Right, so that means it has 26 protons. And if you remember, the number at the bottom is the average atomic mass. So it has units of atomic mass, units AMU. So that basically means 55 0.845 atomic mass units per 1 iron atom. And as we'll see, it also has units of grams per mole. So if you had 1 mole of iron, it would weigh 55.845 grams, right? And since 1 mole is 6.022 times 10 to the 23rd, if you had 6.022 times 10 to the 23rd atoms of iron, it would have a mass of 55.845 grams, right? So again, anytime you see this number at the bottom, always keep in mind it has units of grams per mole, or atomic mass units per atom. So this just shows you the conversion factor, how you can convert atomic mass units per atom to grams per mole and end up with the same exact number, right? So 1 atom of carbon-12 is defined as having a mass of exactly 12 atomic mass units. And we said that 1 mole of carbon weighs exactly 12 grams. That's the definition, right? And 1 mole of anything is 6.022 times 10 to the 23rd. So if we just set this dimensional analysis up, the moles cancel, right? And then 1 atom of carbon-12 has a mass of 12 atomic mass units, according to that definition. So now then what cancels is atoms cancel. And so the unit left is grams per AMU. So 1 AMU is a mass of 1.66058 times 10 to the minus 24 grams. And now if we take that number and use it in the next dimensional analysis, so take the definition for AMU, 1 carbon-12 atom has a mass of 12 atomic mass units, and we just said 1 atomic mass unit has a mass of 1.66058 times 10 to the minus 24 grams, and 1 mole of carbon-12 has this many carbon-12 atoms. If you set that up, AMUs cancel out. Let's see, what else cancels out? This is atoms, not mole. Right, 6.02 times 10 to the 23rd atoms of carbon-12 in 1 mole. So then atoms cancel out, and you're left in units of grams per mole. Right, so 12 AMU per atom is the same thing as 12 grams per mole. So I'm not going to expect you to do this, and I'm not going to expect you to know that. I just don't like throwing things out there and just say, okay, memorize this. I like to show you how it works out as well. So just keep in mind when you see the average atomic mass, keep in mind that has units of grams per mole. Okay, so we can use this to calculate what's known as molecular weight or molecular mass. So that's simply the mass of 1 mole of any molecular compound. So what is a molecular compound? So we'll talk about this in more detail in about chapter 9 or 10, but just briefly, what is a molecular compound? It's basically a molecule where atoms share electrons. So if we take H2O, so if we had an oxygen 16 atom and a hydrogen 1 atom, so it's got 8 protons in the nucleus, 8 neutrons in the nucleus, right, and then 8 electrons. So you can count in blue, there's 8 electrons shown, and hydrogen 1 has 1 proton in the nucleus and 1 electron shown in pink. And I'm just showing you their orbitals overlapping, the electron cloud overlapping, right, to make a bond. Right, so that's a bond. So if atoms' electron clouds are overlapping and they're sharing electrons, then it's a molecule. It's a molecular compound. Okay, but we'll talk about that in much more detail a few chapters from now. Okay, so if we wanted to calculate the molar mass of this, then if we take the periodic table entries for oxygen and hydrogen and take their molar mass. So 1 mole of oxygen has a mass of 15.9994 grams per mole. 1 mole of hydrogen has a mass of 1.00794 grams per mole. But there's 2 hydrogens, so we're going to take the molar mass of 1 hydrogen and multiply it by 2 since there's 2 hydrogens. And we're going to take the molar mass of oxygen and multiply it by 1 since there's only 1 oxygen. And then add those 2 numbers together, and we get 18.01528 grams of water per 1 mole of water. So that's the molar mass, right? So 1 mole of water, how many molecules would that be? That would be 6.022 times 10 to the 23rd water molecules, right? It would have a mass of 18.01 grams. So what does that look like? So that would be 1 mole of water. I added 1 drop of food coloring to it just so that you could see it. So that's what 1 mole of water looks like. So that's 18.015 grams. So there are 6.02 times 10 to the 23rd water molecules in this cup, right? That's a staggering number of water molecules. Okay, so 1 mole of water molecules has a mass of 18.015 grams. For our purposes, we can just take molar mass and let's just round it to 2 decimal places. So 18.02 grams per mole will be fine for calculations. So if we had sucrose instead, so table sugar, so sucrose has this formula C12H22O11. So it's got a lot more atoms than water does, right? And so it's going to have a much larger molar mass. It's 342.3 grams per mole. So this will be what 1 mole of sucrose looks like, right? So that is 342.3 grams of sucrose, table sugar. So how many molecules of sucrose are in this cup? 6.02 times 10 to the 23rd, right? So 6.02 times 10 to the 23rd water molecules and 6.02 times 10 to the 23rd sucrose molecules. Okay, so what's the difference between molecular? So if you notice here, I used molecular weight or molecular mass. That is simply the molar mass of a molecular compound, atoms that are sharing electrons. Formula mass is basically the same concept. It's just used for ionic compounds instead. So this would be the molar mass of an ionic compound. So what's an ionic compound? It would be a compound where the atoms are not sharing electrons. So if we took NaCl, sodium chloride, salt, right? So if you remember, if it's an ionic compound, you always use the smallest ratio of elements in the formula. So it's not Na2CO2 or Na3Cl3, it's just NaCl, right? You always take this smallest ratio. So sodium chloride in the crystal lattice would look something like that. So if you notice, so the sodiums and chlorides are not sharing electrons, but NaCl is really Na plus and Cl minus. It's really a sodium cation and a chloride anion. So how does that come about? So if you had a sodium 23 atom, it's got 11 protons and 12 neutrons and 11 electrons. So I think that's 11 electrons. And then if you had a chlorine 35, 17 protons, 18 neutrons, and 17 electrons, right? So if you mix sodium and chlorine together, basically what happens is one of these electrons from sodium moves onto the chlorine atom instead. And it does so very vigorously, very violently. But that's all that happens is one electron moves from one atom to the other. So they're not sharing electrons. Sodium actually gives up an electron to chlorine. And you make these ions. So now there's 18 electrons here, so it's negatively charged because there's one more proton than electron, but now there's only 10 electrons, right? So it's positively charged. And the two atoms are not overlapping, sharing their electron clouds, so it's an ionic compound. So if we want to calculate the molar mass, it's basically the same thing. You just take the smallest ratio of elements and calculate their and use the periodic table and calculate the molar mass just like we did for water. So sodium, 1 sodium and 1 chlorine, and if you add the two together, what do you get? So 58.4425 grams of sodium chloride per 1 mole of sodium chloride. Or if we just round it, right, 58.44 grams per mole. Okay, so 2 more examples. So we'll do this for glucose, C6H12O6, and for the sodium nitrate. Let's calculate their molar masses. So when you see molecular weight, molar mass, or molecular mass, molar mass, formula mass, it's basically all the same calculation. It's just one the molecular weight, molecular mass is used for molecules, formula mass is used for ionic compounds. Okay, so if we want to calculate the molar mass or molecular weight or molecular mass of glucose, C6H12O6, then we just need the periodic table. So 12.011 for carbon, but there's 6 carbons, so we have to multiply that by 6, right? Because of that, there's 12 hydrogens, so we take the atomic or molecular mass of hydrogen from the periodic table and multiply it by the subscript in the formula, and do the same for oxygen, and multiply those out and add them up. And you get 182 points. No, that's not right. You get 180.16 grams per 1 mole of glucose. So you should get accustomed to writing it like that. You putting the grams per mole, grams of the molecule and moles of the molecule in when you write it. Okay, so if we do the same thing, so if you know how to name that compound, that would be nickel 2 nitrate, right? So transition metals, you have to have the Roman numeral in the name. So how many nickels are there? There's only 1 nickel, so we use the periodic table, 58.6934 grams per mole for nickel, and there's 1 nickel. So how many nitrogens are in the molecule? So what you have to recognize is the 2 here extends to everything inside the parentheses, and only what's inside the parentheses. So it extends to the nitrogen, so there's 2 nitrogens. So we would take the 14.0067 from the periodic table, multiply by 2, and then how many oxygens are there? Well, there's 6 oxygens, right? So basically you take the number, you take the subscripts and multiply them by each other, and that's how many of each of the different elements there are. So if you multiply those out and add them up, then you would get 182.70 grams of nickel 2 nitrate per 1 mole of nickel 2 nitrate. Okay, so we'll stop there. Hopefully that makes sense.